Hello and welcome to the channel of Sigma Plus Industrial Solution. In that video, we're going to talk about the calculation of the sample size with a known standard deviation of a population. And we're going to discuss about the level of the confidence. Please remember that under the condition of the sample, the standard deviation of the population is known or unknown. There is a big difference in calculating the sample size. There will be another video where we are going to explain the calculation of the sample size in case that the standard deviation of the population is unknown. Okay, maybe some of us don't know that if we collect different samples from the same population, that we might observe different characteristics, different results in between the samples. And this is something normal, because this could be due to the what we call the sampling errors. But let me give you an example. Before that, I want to explain the two vital factors when you collected a data sample. So imagine, for example, that you are conducting a statistical study about the average height in a certain city where the population is about 100,000 people. So what you have done is that you have collected different samples, maybe 4 samples, and then you have found that each sample has a different average value. That's again something normal and natural, because this could be due to the what we call the sampling error. But whenever you are collecting data for creating samples and conducting statistical study, you need to take in consideration 2 vital factors. The first one is the sample size. So as all of us know, that the larger is the sample size, the more accurate will be the results, and the lowest would be the error percentage, right? But do not ever forget that there will be an associated cost, an increase in the time for collecting the samples. And that's why it's so important to calculate the optimized sample size. Okay, so you can control the time and the cost of the resources. The second vital the second vital factor is represented in the criteria of data collection to ensure that we have collected the data in a random way. And what do I mean with a random way? That it's very important to ensure that each member in the sample has been taken with the same chance of the other members. Or in other way, every member in the population has the same chance in being selected, and there is no way for bias selection or selection for a certain purpose or specific interest. Okay? Let's take a work example to better understand now what do we mean with the confidence interval of a sample means. So suppose in the there is a Ministry of Transportation that wants to improve the vehicles movement flow in a critical highway to reduce the delayed times of employees in reaching their job sites. So one of the information that they need to know is to describe the average movement of the car in that highway. So assuming that the population standard deviation is 15.5 kilometers per hour, and the required confidence interval to conduct that statistical study is 95%. For supervisors, we are assigned to measure the vehicle's speed with 4 different samples, and the results we have collected as per the shown table. So we have the table here where we have the 4 samples of measurements of the vehicle speeds. Each sample contains 15 readings for the vehicle speeds in the highway. And the first observation that we can see that there is a difference in the value between each sample. So the average value for the first sample was 101 kilometers per hour, The second one was 88.9 kilometers per hour. The third one is about 95 kilometers per hour. And the fourth one was 111.8 kilometers per hour. And we will consider that those readings had been collected in a random way. Okay, so as the first result or the conclusion from that I can get the average value, which is 99.28, the average of the 101 and 88.9 and 94.8 and 111.8, which is the 99.28. So what I'm interested to know now is the range of the population mean. What do I mean with that? You see, whenever I speak about a factory, I cannot say that this factory is producing 10,000 cars per year, okay? Because it's not fixed counted. There will be a variation, right? So I can say that this factory is producing on annual basis between the 9,000 to 10,000 cars per year. Okay, so the 9,000 to the 10,000, this is the average value. Okay, this is the range of my population mean. Sometimes the factory might produce 9,200, sometimes 9,700, or any value between the 9,000 and the 10,000. Like our example, we want to see the range of the mean value of the speed of the cars. So it could be something between the 80 to 100. We don't know yet. So this is what we want to calculate with a confidence level of 95%. And the next slide, I will explain what do I mean with that. But for now, what we need to know is to know what is my margin of error. So the tolerance between the mean value and the upper and the lower value is known to be the margin of the error. And we are going to see how we can calculate the margin of the error so we can construct what we call the confidence interval. Okay. 95% confidence level. What do I mean with that? As simple as it. Imagine if I ask you to collect 100 samples instead of the 4 samples. Okay. And you get out the conclusion of the average velocity for each sample. 95% confidence level means that there is 95 samples. Their average will be dropping in the range of the population mean. So, as an example, when I said that the average speed of the cars in that highway is between the 80 kilometers per hour and the 100 kilometers per hour. So, the 95% confidence level means that 95 samples means will be dropping in between the 80 and 100. And only 5, no more than 5 samples will have readings or values of the speeds of the vehicles outside the 80 to the 100. Could be 70, it could be 110, something outside that tolerance. So there is a risk of error of 5%. So a 95% confidence level means that if we collect 100 samples of measuring the car velocities, 95 samples will contain a mean value that drops in the population range of the means, and 5 samples out of the 100 samples will not capture the population mean. So as you can see, this is if we consider this is the distribution curve of the population, then the 95%, the shaded area is representing the 95%. If I take any samples out of that population, we will see that 95 samples, their average point will be dropping in the range of the population mean. So as you can see, maybe this one is dropping in exactly with the population mean. The mean of the second sample is also dropping somewhere inside the range. The third one you can see is also dropping inside the range of the population mean. Also, the fourth one is dropping inside the range of the population mean. But if we look to this one, the green color, it's dropping outside. the population mean. So that's what we mean with a confidence interval or confidence level of 95%. We usually utilized what we call the z-score to calculate the number of the standard deviations away from the mean and under the confidence level. And give me a minute, I will explain to you how do we utilize the z-score to calculate the margin of error. Okay, so refreshing back the empirical rule, if we remember the empirical rule, because we are considering that the data distribution of any process is a normal distribution unless there is an assignable cause. And remember always that if your data distribution is not a normal shape, then you cannot implement those rules. Referring back to the empirical rules, or what we call the 68 and the 95 and the 99.7 rule, which stated that 68% of the data are falling within one standard away from the population mean. And 95% of the data are falling within 2 standard deviations away from the mean. And 99.7% of the data are dropping within 3 standard deviations away from the mean, as you can see. So if we count here, this is 1 standard deviation, this is 2nd standard deviation, the 3rd one, and again from the left side, -1 standard deviation, -2 standard deviation, and -3 standard deviation. Okay. Now, when we collect the average of each sample and we draw a distribution curve, it will construct a normal Bell distribution curve. So that's why we can implement the empirical rules in finding the range of the population, the margin of the error, the confidence interval of the sample mean. Okay, so in our example, what we are interested to know is the confidence interval for this, the sample that we have collected, and the margin of the error at 95% confidence level. So what do we mean with the 95%? It means that if I write my average speed that we have collected, which was 99.28, so I write here the 99.28 with a level of confidence of 95%. I want to know what is my margin of error. So my 95% is the area under the curve with 2 standard deviation approximately, right? So this area is my area of interest. Okay, and to define the margin of error, the first thing that I need to know is to calculate the z-score. And the z-score, it has a definition which is it's telling us the number of standard deviations for any point away from the mean. Okay, so let me just erase some of the things that I have drawn here, and let me explain to you in a better way what do I mean with that. Okay, so if I stop here, my z-score from the sample mean is almost -1, -1.5 standard deviation. If I stop here, then the z-score is the distance in standard deviations from the sample mean. So it will be approximately about 2.5 standard deviation. This is what we mean with the z-score. But what we are interested to know now is to know what will be the z-score and the 95% confidence interval. So where are the points that I am interested is those points. Okay, that's this is the level. If you remember my area of the 95, this is the limits of the 95. So as per the empirical rule, it should be something around the -2 and 2, right? This is the z-score that I have. Okay, but in statistical way, we will see that there is a slightly different in the real value of the z-score. Okay, but how can we calculate the z-score more accurate? We need to go to the z-tables, and that's what we are going to go. So the first point that we are going to calculate, we want to calculate the z-score from the left side of the mean, and then we will calculate the z-score at the right side of the mean. And just by looking initially, I can say that the z-score is on the left side is about the -2, and the z-score after the mean is about the 2 standard deviations. But let's go to the z-table and see how can we conclude or to find the real value of the z-score. Okay, so for the first area that we are going to look is first of all, we have taken a confidence level of 95%, right? So if I divide, so that means that the alpha, which we call it the significant value, is 5%. And those 5% will be distributed by 2.5% in the left side and 2.5% on the right side. Okay, so if I will go to the z-score table, I will go first of all to see what is the z-score at this area. So I will be interested to know the z-score at that area. So I will consider the area under the curve where I have highlighted is 0.025. Okay, and then I will go to check the z-score by taking in reference the area under the curve, which is 97.5. Why? Because this is the 95%, right? From here to here. And then I have plus the 2.5%, which is the 97.5. And from there, I can know what is the z-score on the right side of the mean. So first of all, we need to know what is the z-score at that point at the left side, where the area under the curve will be 0.025. Okay, so let's go. So the first point, when I'm looking to the z-table, what you can see, under this table, this is the probabilities area. And in the vertical column, this is the first 2 digits of the z-score. And then this is the second or the next digit of the z-score. Let me explain it to you in a better way. So let me erase, and then we return back. And then, so the first information that I know that the area under the curve that we want to see is the 0.025. So where is the 0.025? Here it is, as it is highlighted. So I will go horizontally, and my first number is -1.9. Then I go to vertically, so it's 0.06. So my z-score will be -1.96, which is very near to the -2 standard deviation. Okay, now there is no need that you go to the z-table to find the other z-score because it's symmetric. But in some cases, if the probability of the area or the percentage of the area that you want to measure is not symmetric, then in this case you need to go to check the z value on the right side of the mean. But here, since it is symmetric, I can conclude easily that the z score on the right side of the mean will be simply plus 1.96. But again, there is no issue to repeat the same steps again. So in that case, we will go to the area where the area under the curve is is 0.975 or 975.975. So I have here, this is the area under the curve, 0.975. And then the z-score, I will go horizontally. I have the plus 1.9 and vertically the 0.06. So my z-score will be plus 1.96. Now, I know the z-score is plus and minus 1.96, and I want to know what is my, and I want to know now what will be my margin of error, the tolerance of the average value of the population. Okay, so we can start to draw my Bell distribution curve, and my average value is 99.28 kilometers per hour. Now I want to know what will be my minimum margin of error and the maximum. And to do that, we can start to implement the formula of the margin of error, which is the z-score multiplied with the standard deviations of the square root of n, where n is the sample size. This formula is known to be the standard of the error, okay, where the sigma is the standard deviation of the population. Okay, so now we can plot our equation where we have the z-score is plus and minus 1.96 multiplied with the standard deviation of the population, which was 15.5, divided by the square root of the sample size, which is 60. So based on that, the margin of error will be plus and minus 3.92, which is plus or minus 4% of the average value. So based on that, I can conclude that the range of the population mean will be something between the 95.36 to the 103.2 kilometers per hour. So again, if I collect 100 samples of readings, 95% of the samples will contain an average value that is dropping between the 95.36 to the 103, and there will be 5% only risk of error. Okay, now let's do this exercise backward. What do I mean with backward? I mean, suppose that you want to control the percentage of the error, the margin of the error, and based on the margin of the error, you need to calculate the sample size. Okay, so in the first example, we didn't give a condition about the error percentage, but in that example, what I want to do is that I want you to calculate the sample size that needs to be collected from the supervisors in such a way that the level of the error or the margin of the error, instead of that it was plus or minus 4%, no, I wanted to have it plus or minus 2%. So for the previous example, suppose that you are a statistician and you were requested to define the sample size for collecting the car speeds in such a way that the confidence interval should be no more than plus or minus 2%. So let's see how we can do it. If you have understood the first example, it will be very easy for you to understand that one. Okay, so again, this is the formula of the margin of the error. The z-score multiplied with the standard deviation of the population divided by the square root of the sample size. So this one, the margin of the error that I need is plus or minus 2%. So if I repeat that equation, 0.2% multiplied with to the average value of the speed, right, equal the z-score, which is 1.96, multiplied with the 15.5 divided by the square root of the sample size. So that will give me at the end result that the sample size that we need to collect is 234. So that in this case, when I collected the sample size of 234 readings for the vehicle speeds, I will have much more accurate for the values of the speed of the vehicles in such a way that the percentage of the error and the margin of the error, instead that it was plus or minus 4%, it is now plus or minus 2%. So what you can conclude here, that whenever you want to have a very lower percentage of the error, then indeed the sample size will increase. Because the first time the sample size was 60, but as you can see, now the sample size increased to 234. But again, do not ever forget that whenever you need to increase the sample size, you will have to spend more cost and time. At the end of that exercise, I hope that you could understood how to calculate the sample size for unknown standard deviations for the population. And see you for the next time, where we are going in the next video, where we are going to explain how to calculate the sample size for a population that we don't know its standard deviation. I thank you for your good listening and watching, and see you for the next time. Thank you.